thermodynamics. So first, classical thermodynamics. Thermodynamical temperature T proportional to PV when P tends to 0, and Kelvin temperature is the ratio between this limit PV at temperature T divided by PV at temperature of triple point. The first law of thermodynamics will follow this equation: dq equal to du plus pdv dw. This d bar indicates that it is not a state function. The second law of thermodynamics is ds equal to dq by t, and entropy is always increasing. Thermodynamical work: in case of hydrodynamics, we have dw equal to minus pdv. Surface tension, so gamma dA, gamma is a surface tension times the area. In case electric field, E dot dp, dp is the induced electric dipole moment. In case of magnetic field, we have B dot dm, dm is induced magnetic dipole moment. Electric current, that is the force, the potential difference delta q times the charge movement. So different cycles for Carnot cycle, the heat input and work extract. So the ratio between them is the efficiency eta. So Th minus T1 by Th. Th is the higher temperature. So 1 minus T1 by Th is the heat for heat engine. For refrigerator, we extract heat. So heat extraction divided by work done, that is T1 by high temperature minus low temperature. So T1 by Th minus T1. For heat pump, we supply heat using heat pump. So T high divided by T high minus T low, or T1. In case of Otto cycle, we have V2 by V1, that is the compression ratio. Now heat capacity at constant volume is dq by dt. So in that case, at constant volume, so this term goes to 0, so du dt at constant volume, or in terms of dq we have tds, so t ds dt at constant volume. So at constant pressure, Cp is equal to dq dt. So Tds at constant pressure. Difference between heat capacities Cp minus Cv equal to Vt beta square by Kt. Kt is the isothermal compressibility. Ratio of the heat capacities is gamma Cp by Cv. That is the ratio between isothermal compressibility and adiabatic compressibility. Thermodynamic coefficients: isobaric expansion beta is equal to 1 by V dV dt. For compression, we need pressure. For expansion, we need temperature. So at the bottom it is temperature. So isothermal compressibility minus 1 by V dV by dP. Adiabatic compressibility, so the difference is only in case of adiabatic we have entropy, here it is temperature. Isothermal bulk modulus is K of T equal to 1 by kappa T, that is the inverse of the KT, kappa T. Similarly, adiabatic bulk modulus is 1 by kappa S. So we can also compare with this elastic modulus equal to stress by strain. So force per area will be the unit of the compressibility, unit of the elastic modulus or bulk modulus here in this case. So the unit would be pressure. So in both of the case we have pressure unit. So expansion process. So in Joule expansion, we have two container, one with a separation between them, and we will remove separation and the gas will freely expand. So the Joule coefficient in that case dt by dV at constant internal energy, and Joule Kelvin expansion dt by dP at constant enthalpy. We will get the following expression. For constant energy, internal energy, we have minus P and dP dt, and for constant enthalpy we have V and V, and there is a difference, constant volume and this is constant pressure. So ultimately eta is minus 1 by Cv times T dP dt minus P for Joule expansion. For Joule Kelvin expansion, so 1 by Cp T dB dt minus V. So internal energy can be expressed from this relation. So dq equal to du plus pdv minus mu dn. Enthalpy is internal energy plus pv. Helmholtz free energy, internal energy minus Ts gives free energy is free energy plus PV. Grand potential is free energy minus mu n. Now Maxwell relations. So we will remember the relations using the following method. Should S poses to verify. So S P T V, whenever it will go in clockwise direction, we will take positive sign. So first thing, Suresh positive direction, so poses P T V. So if we get this relation, we will use it. So let's say Suresh poses to verify. Suresh poses to verify. So this is the third relation. In case it is reverse direction, Suresh poses to verify, there will be negative sign. So del S del P, del S del P, the fourth relation, del P equal to dV dt. Again for the other two cases, to verify Suresh poses, in that case we will have positive sign. So dt dp positive sign. Again we will have, so to verify Suresh poses, so this will have minus sign. So this is the first relation. So Gibbs Helmholtz equation, U equal to minus T square delta of F by T. In case of U, we have F by T by dt. For Gibbs free energy, we have minus V square del F del V by dV. In case of H, we have minus T square del G del by del T del G by T by dt. Now phase transition, heat absorption is the T times difference of the entropy. Clausian and Clausius-Clapeyron equation for first order phase transition, we have dP dt equal to L by T times delta V. For NN first equation, for second order phase transition, dP dt equal to, it is the ratio between the difference of isobaric expansibility and isothermal compressibility. Gives phase rule P plus F equal to C plus 2. Gas law, so Boyle's law, PV equal to constant. Equation of state, PV equal to nRT. Adiabatic expansion, P V to the power gamma equal to constant. For adiabatic, for temperature and volume, TV gamma minus 1 equal to constant. T to the power gamma, P to the power 1 minus gamma equal to constant. Delta W equal to P1 V1 minus P2 V2 divided by gamma minus 1. Internal energy equal to nRT by gamma minus 1. Reversible isothermal expansion delta Q equal to nRT ln V2 by V1. Delta S equal to nR ln V2 by V1. So you just compare the first term in the equation. So dimension of S equal to nR or capital N kb. Dimension of energy equal to nRT. By the virial expansion, you have Pb equal to RT times 1 plus beta by V plus beta B by V square. Similarly like this. Whenever the first coefficient is 0, it is called boil temperature. So beta 2 T equal to 0. Van der Waals gas, we have P plus AN square by V square times V minus NB equal to nRT. So for a single mole gas, P plus A V square times V minus B equal to RT. So we can extract the critical temperature by dP dB equal to 0. So after doing that, we have Tc equal to 8A by 27 RB, Pc equal to A by 27 B square, V equal to 3B. So the ratio of Pc, Vc, RTc equal to 8 by 3. The reduced equation of the Van der Waals equation, we can replace P reduced equal to P by critical, V by V critical, T by T critical. We will replace that, and we will replace also Pc as A by 27 B square, and similarly others will get the following relation. So in case of Van der Waals equation, we have plotted PR and VR. Will get this following curve for different T values. Now kinetic theory of gas. Pressure P equal to 1 by 3 Nm C square. N is the number of density, M is the particle mass. Equation of state for ideal gas, Pb equal to nRT. Internal energy is 3 by 2 nkt. Cb equal to 3 by 2 nkt. Cp equal to Cb plus nkt. Or using the degrees of freedom, F by 2 nkt is the Cb, and F by 2 plus 1 nkbt kb equal to Cp, and gamma equal to Cp by Cb equal to 5 by 3. In case of entropy, S equal to nkb ln V e to the power 5 by 2 by n lambda cube. So here lambda is the wavelength scale, h root over of 2 pi m kbt. Maxwell-Boltzmann distribution, we have Pc from C to DC, C plus DC, we have m by 2 pi kbt to the power 3 by 2 e to the power m by 2 kt c square times 4 pi c square dc. Particle energy distribution, Pe equal to e to the power minus half e to the power minus e by kbt de, and temperature is T to the power minus 3 by 2. Mean speed is 3 by 8 pi by 8 pi times kbt by m to the power half. Mean speed, RMS speed is 3 kt by m. Most probable speed is 2 kt by m. So RMS speed is larger than average speed, and it is larger than the most probable speed. Transport properties, L equal to 1 by root over 2 pi d square by n. D is equal to molecular diameter and n is the particle number density. Survivable equation, P probability equal to e to the power minus x by L. Brownian motion, mean square displacement equal to kt by ktt 3 pi eta a. Gas equipartition, individual degrees of freedom will get half kbt. Cv equal to f by 2 n kbt. Cp equal to f by 2 plus 1 n kbt kb. Gamma equal to Cp by Cb equal to 1 plus 2 by f. Statistical entropy, in the Boltzmann formula, S equal to kb ln w. W is the number of accessible microstates. For Gibbs entropy, S equal to minus k pi ln pi. So for two level system, W equal to n factorial divided by n minus small n factorial times small n factorial. So Z equal to e to the power minus beta ei. Canonical ensemble, pi equal to e to the power minus beta ei divided by Z. Grand canonical partition function, xi equal to e to the power minus beta ei plus beta mu n. For grand canonical partition function, pi equal to 1 by xi e to the power minus beta ei plus mu n ni. So Helmholtz free energy, F equal to minus kbt ln z. Grand potential phi equal to minus kbt ln xi. Internal energy U equal to F plus Ts or F equal to U minus Ts. From that we can write U equal to F plus Ts, that equal to minus delta dy d beta ln z. Entropy calculation, pressure calculation and chemical potential calculation can be done through this. dq equal to du plus p dv minus mu dn. So dq equal to t ds. So again F equal to u minus ts. So df du minus tds minus std. So we replace du minus tds with du minus dds equal to df plus std. So df std plus p dv plus mu ds. So whenever we will calculate s with s, then we will have to derive with respect to df dt. So minus df dt equal to s. Similarly p equal to minus del f del v. Again mu equal to plus del f del n. So for identical particle, for Bose-Einstein distribution and Fermi-Dirac distribution, we have Fi with respect to different EIs. We have saturation for below whenever EI equal to 1, but for higher values of beta we have starting of the Fi is not 1 but less than 1. So Bose-Einstein distribution, Fi equal to 1 by e to the power beta ei minus mu minus 1. For Fermi-Dirac distribution, 1 by f beta epsilon I minus mu plus 1. So there is minus and here is plus. So Fermi energy EF is proportional to n to the power 2 by 3. Bose-Einstein condensation temperature is also proportional to n to the power 2 by 3. Population density, so this can be written like this: n number of states equal to g mj e to the power minus e by kbt. So using that formula we have the ratio between n mj and m lj. Partition function z also summation over all I. Shaha equation is like this, and Shaha equation for ion population, and for general we have these two relations. So fluctuation and noise, we don't need that. Radiation process, photometry, radioactive transfer, black body radiation, we need little bit of this. So lambda t, Wien's displacement law, lambda t equal to 2.9 into 10 to the minus 3 millikelvin. Stephen Boltzmann law, m equal to sigma t to the power 4, or energy density U equal to U proportional to t to the power 4.